Let's finish up this example where we're sketching y equals 2x squared over x squared minus 1. In the previous video, we found that the function was increasing from negative infinity to 0 and decreasing from 0 to positive infinity. We also noted in step 6 of the previous video that we did not have continuity of the function f near plus or minus 1, so we could not use the first derivative test for local minimum or maximum at x equals plus or minus 1. But when x is equal to 0, we do not have a discontinuity in the original function, y equals 2x squared over x squared minus 1. So yes, we're able to use the first derivative test, and we find that there's a local maximum at x equals 0. So we're picking it up now at step 7, where we're going to do the test for concavity. Second derivative is derived by looking at the first derivative from the previous video and using the quotient rule. You'll notice that we're going to be able to factor out of the top, out of the numerator, a factor of x squared minus 1 to cancel with a factor in the denominator. So when we're finished simplifying, we get x squared minus 1 to the third power in the denominator, which can be factored further because we've got x squared minus 1. We break that up to x plus 1 times x minus 1, each to a factor of 3. Set the second derivative equal to 0 and solve. That means the numerator has to be equal to 0. So 3x squared plus 1 equals 0. Solve for x. We're going to get x equals plus or minus a negative number. That's imaginary. That's not real. We can't graph it. We can't use it. So looking for this, these values of x that are going to be the critical numbers of f prime, we're not going to be able to use numerator. The numerator just gave us something that wasn't real. So we're only going to be able to use the zeros of the denominator. So take each of the factors in the denominator and set them equal to 0 and solve for x. That gives us x equals negative 1 and x equals positive 1. Okay, look back at note 84 to refresh your memory about what I mean when I say critical numbers of f and critical numbers of f prime. All right, let's bust up the number line using these critical numbers of f prime that we just found. And let's use them to get a sine graph of the second derivative in the different regions between negative 1 and 1. And the three regions, we get a positive value, a negative value, and a positive value for the second derivative. That means we get concave up where it's plus and concave down where it's negative. Okay, so concave up here from 0 to negative 1, from negative 1 to 1 concave down, concave up from 1 to infinity. We have a point of inflection at x equals negative 1 and x equals 1. So now we're ready to sketch. Here's our y-axis and our x-axis. Let's see, at negative 1 and positive 1, we have 2 because we have a horizontal asymptote at y equals 2. We have 2 vertical asymptotes at the zeros, negative 1 and 1. And then if we graph some points, we can see that we have this situation that I'm graphing now. And it satisfies all the conditions that we found. We have the function increasing in this region, and we have it, let's see, decreasing on the right. We have it increasing from negative 1 to 0. We have it decreasing from 0 to 1. We also have, let's see, we have a local maximum at 0, 0. We have a point of inflection, 2 points of inflection at x equals negative 1 and x equals positive 1. So everything checks out with what we found in the previous steps.